Dando início à transmissão dessa tarde, vamos ter o prazer de escutar e apreciar a palestra do senhor Bernardo Aubé, que é um engenheiro químico com 29 anos de experiência em tratamento de água de mina. Ele tem mestrado em engenharia ambiental e tem trabalhado em todo o mundo resolvendo problemas das águas de Minas. E realmente gosta de enfrentar novos desafios e compartilhar o seu conhecimento acumulado. Ele vai ministrar a palestra A Importância do Planejamento de Tratamento e Manutenção da Água de Mineração. Com a palavra, o senhor Bernardo Aubé. Okay, you can start, Bernardo. Yes.
Thank you. Muito obrigado. I apologize, no falo português. So, as Flavio gracefully presented, I will talk about the importance of planning and mine water management and treatment. So, a little bit about myself. I've been working 29 years in mine environment. My first 10 years, I worked at the Noranda, it's now Glencore Technology Center. And for the past 19 years, I've been working as a process engineer and consultant. During that time, I've done all different parts of mine water treatment all over the world. And I've seen all different stages as well, working from mining projects to new mines, operating mines, mine closure, and published on all of these. And I'll be giving some examples of each of these as we go through. So just a bit of background. Water in mining is everywhere. And most types of ore that you're going to be mining, water is used in the recovery. So your mill has a lot of water, whether it's iron, whether you're doing flotation for heavy metals, or whether you're doing gold or silver recovery, even diamond mines. All of these mines have excess water. Most of these mines actually have excess water and must discharge the environment. Some of these mines are in arid areas and must recycle as much water as possible. But whether they recycle or they discharge, you have objectives that have to be met. And this water, wherever it is, it has to be pumped, it has to be stored, it has to be treated, and must meet these objectives. This is a little bit of an aside that is not directly representative of mine water. The social license to operate is very important in mining, not only for a specific mine, but also what happens at one mine can affect others. Water management in mining is one of the key factors in this social license to operate. And if you have a significant event at one location, if it's for a large mining company, this could affect the social license to operate at other company sites throughout the world. But it also affects the view of the entire mining community. So owners of a mine must therefore be careful not to take too much water that will affect other stakeholders, other water users in the area, not have spills or non-compliance events, not cause any environmental impact or toxicity, and not affect public drinking water. And affecting public drinking water is not necessarily toxicity. It can be hardness downstream of a mine that can be causing some issues. So mine water planning, where is that water? Well, first, most mines have potable water and sewage water that have to be dealt with. I don't talk about that in this presentation because these are small volumes. So the rest of the water, the larger volumes, the input, well, you've got the precipitation, which when it falls on your mine site, becomes contact water. You've got the mine groundwater. So whether it's open pit or underground mine, you have mine dewatering. You have seepage from your tailings and waste rock. And you also have the fresh supply that is used often for reagents, pump glands, And then in the process, you have the use of water. There's a lot of water in milling, flotation, and then you have water storage, whether this is a tailings pond or separate ponds. Recycled water is water that goes with the tailings and then comes back to the process. And you have the water that must be discharged. So water planning, I mean, you're going to hear these two words a lot, quantity and quality. That's what water planning is. You have to know for each of these how much you're going to get, what quality is it going to be, or what quality do you need it to be? And planning is determining how you manage all of this. So we're going to talk a little bit, 2 slides about objectives. So the recycle water objectives are related to the process. I mean, this is about flotation, for example. If your water has certain chemicals, it can be difficult to do proper flotation. If you have a high calcium and sulfate and you get gypsum scaling, that can be a significant problem with your piping all over the place. Toxicity, if you have thiosalts in your water, thiosalts can generate H2S when it's in stagnant water, and that could be toxic to the employees. So that's the main things you have to look at for recycled water. For environmental discharge, this is generally determined by regulators, but sometimes can be affected by community pressure, or an internal large company can have their own objectives. By regulators, these limits continue to be more stringent all over the world. The levels are being brought down, and additional parameters are being added also pretty well yearly, at least in some locations, definitely yearly. So as far as water treatment goes, there's new technology that allows you to do better treatment. But despite this, mine water management is not becoming more simple. It's still becoming more complex. Part of it is because you have these technological advances, the stakeholders, the communities, expect you to do it. And also you have mine water management tools that are used not by everybody right now, by a minority of operators, and these can be pretty complicated to use. So that's a mine water quality. Now, water management objectives, well, you want to minimize the amount of water that you have to treat, and you want to maintain clean water clean. So you ensure the diversion of all uncontaminated waters to both reduce the treatment volumes and to not affect as much water. But all contaminated water itself has to be picked up. So how do you minimize the amount of contaminated water? If you have to pick it all up, is you minimize the footprint as much as possible, which will minimize the contact water. Another thing that you can do is if you're in operation and you have a waste rock pile or tailings that are no longer being used, you can start covering this. So that's progressive reclamation. And this will allow you to have a bit less contact water. Now, this is a conceptual. I have only two actual slides that are technical. This is not a technical presentation. This is more of a philosophical presentation. And this slide here is one of the two that shows, for example, a tailings repository on a slope with a dam. And what is in red is what needs to be collected. So it's contact water that goes through the tailings and could go underneath the dam and be collected in the seepage. This is a cross section, and on the top, you see the ditch and berms that would be built here to ensure that the clean water is diverted, not in contact, and does not have to be treated. This is a tailings, but it could also be a pit. It could also be a mill site. So I'm going to talk some more about quantity and quality. The objectives are the easiest part. I mean, most of the time, the regulators tell you what you need to do, and that's pretty easy. So the key is actually the raw water quality and the amount of water that you have to deal with. Now, there are challenges at all stages. I divided the stages into 4. the mining projects before they're built, the new mines, so the first couple of years of operation when they're built, the operating mines, and the closure of the mine. The way that I'm going to show this, I have a number of examples and a number of slides that are going to give some idea of what can happen and what needs to be done. So as far as mining projects, I'll talk about the typical focus of what a mining project is and give an example there. In the new mines, I'll talk about the consequences of insufficient planning and the right way to design the plant and how to avoid these consequences. And one typical new mine example. Now, what you do in mines, for new mines, the mine planning occurs in the project stage. So I'll make that clear as we go on. For the operating mines, there's 3 examples with the consequences, how to avoid the water issues in operating mines, and then mine closure has 2 examples. So for the mining projects, and this has nothing to do with the mining project, it's just a pretty picture. But when an ore body is discovered, the owner is focused on turning this into a mine. You know, you got to do your feasibility, you got to obtain the funding. So what do? You delineate the ore, you find out how much ore is in there, how much gold, how much nickel, whatever it is you're mining, iron. Then you prove the metallurgy. Proving the metallurgy means doing pilot tests, often for flotation or cyanidation. You plan your mine workings, your waste rock and tailing storage, access and infrastructure, power, bringing power to the plant. All of these are the big costs that you have to do your feasibility. But often at the mining project stage, I don't know how many times I've heard this. At this point, we'll just put $5 million aside for a treatment plant. It is not that simple. And I'm going to explain how it's not that simple. Here's one example. This example actually occurred in the project stage. All of these examples are real. So mining engineers designed an open pit mine. This was actually an iron mine and placement of the waste rock. And it was, competent mining engineers. The plan was very good. The costs were all developed to do a good economical and safe placement of waste rock. But they never involved water experts until late in the feasibility stage. This is right when the mine operator wants to get the funding. And they just said, oh, we better get a water guy on here. And then you look at this and you see that the waste rock actually spans 3 watersheds. Now, this isn't the fault of the mine engineers really, because it's just where the ore body was located. I don't know why that often is, but ore bodies always seem to be located at least 2 watersheds. And it was also too close on this side. So on one side. So looking at the water management, you saw that, the suspended solids that would come for this, you need to have some large ponds at the toe of your waste rock or some ditches that go to a large pond. In this case, because it's 3 different watersheds, you can't have one single pond and ditching. So you have to have 3 ponds, and one of them is too close to the river. So looking at this, this forced a redesign of the waste rock plants and also the added design of large ponds, causing important delays in the feasibility and increasing the cost of the feasibility. And no owner wants to be spending a lot of money in feasibility before you even have the mine start construction or before you even have the funding. So that $5 million budget that was put aside was not sufficient, especially considering the ponds that had to be built. So what happens in a new mine? Often a new mine, you get a surprise. All of a sudden you find out water treatment is needed. And it's needed now because when you realize this, your water inventory is high. Your tailings pond is full of water, or your raw water pond is full of water, and your water quality does not meet the objectives, and you don't have a treatment plant that is designed to take care of this. So you don't have the time to do all the studies, and I'll talk about what these studies are. And you don't have the time to hire a good water expert. What's the result? You have a panic plant. You have to build a plant, and you have to build it now. So here's an example of a panic plant here, where it was built using material or equipment on site for a temporary urgent fix. But what often happens though, in the first year or two, is that the engineering company that was hired to do the design and startup of your mill, your concentrator, are still there. So you have some good process engineers, chemical, mechanical engineers that are there on site. And so they know, pumps, they know water, but they don't really know anything about mine water treatment. So they, based on literature, they build something. So this is used equipment. Another thing is you don't really have time for permitting. For proper permitting, you need to design everything, go for the permit, and promise what is reasonable and within the limits. And another thing that often happens is you just go straight to supplier and you say, I need something now, and the supplier supplies something immediately. Now let's talk about water treatment suppliers. I'm not here to cut anybody down, and I'm not here to be competitive, and there are some very good suppliers out there. But some suppliers are not as reliable, and you don't necessarily know this. Some suppliers will just say that their equipment can do it no matter what your problem is. So essentially, suppliers, they'll promise anything just to sell something. And then you say, well, it doesn't matter whether it's the right equipment for the job or not. They give me a guarantee. But guarantees can always be disputed and really hard to prove in court. And I'll talk about design criteria later, but really your design criteria, you need to have them know exactly what your quality and quantity is going to be and make that in the guarantee. Make sure it's included in the guarantee. And some very good and very well-meaning suppliers can only sell what they provide, which is not necessarily exactly what you need. So this equipment may work, but the capital costs might be a lot higher than necessary, and the operating costs are almost always higher than necessary. So really what you need is a custom solution, but a custom solution is not done away from the suppliers. The suppliers are also included. The suppliers, the clarifier systems, the pump skids, the reagent systems and filtration systems, all of these things come from suppliers. And you got to work with the suppliers to get the best custom solution for your needs. So what happens when you do the panic plant? Now, I'm not talking specifically when you're dealing with suppliers, but in the end, what happens with a panic plant is because you don't take the time, it's probably going to cost a lot more. You have to order things at the last minute, and often with any supplier, if you put a rush, it can cost 20% more to get the equipment that you need. The operating cost may be a lot higher than what would be expected in a good custom plant. The sizing, well, if you didn't do your studies, maybe you cannot meet your high flow events. So this is a 1 in 100 rain event, or in Canada, it can be in the thaw during the spring freshet. And these plants can use the wrong reagents. The equipment can be the wrong type of agitators and the wrong types of pumps. So it doesn't work so well, and you have a lot of maintenance and a lot of downtime. You can have your sludge can be a very low density when it would have been possible to make a high density sludge, which is more stable. So your waste disposal costs increase. Worse than this, the plant may not meet your treatment needs and you have non-compliance. And non-compliance can mean fish kills, can mean government fines, bad press. You're affecting your social license to operate. Now, obviously, the worst case, and we've seen this at several places around the world, including in Brazil, is sometimes the water is held back because it's not in compliance, and this can lead to dam breakage. Let's not go there. So what is the reason for the panic plant? Where does this water come from that has to be managed at the last second? Well, very often in the past was unexpected acidic drainage. That means that when the mine was planned and built, it wasn't recognized that the sulfide content, pyrite and pyrrhotite often are the culprits, that they would cause acid drainage. I would say since the 1990s, definitely since year 2000, this is not seen as often. Normally there are acid-base accounting done, there's humidity cells, and these things will let you know if you're going to have acid drainage. What happens still more often is neutral drainage with a contaminant. So you do your acid-base accounting, but if you have small concentrations of nickel, selenium, molybdenum, arsenic, these are all still very mobile at neutral drainage. Sulfate and suspended solids is irrelevant to pH. Processed water, well, processed water, if you have a nickel mine and you're recycling your water, your sulfate content may continue to increase as it's discharged in the flotation. Same with a gold mine, cyanidation, you have sulfate that's released in your leach tanks. At a gold mine, you also use cyanide, and when you destroy cyanide, you convert some of that to ammonia, and that can be an issue and cause you to have a panic plant. Thiosalts generation is often not seen from the beginning, but that's another thing that can cause a panic plant. And in groundwater, sometimes you have high salinity, you have a sulfate content that can exceed your limits. And if you don't measure that ahead of time, that can cause a panic plant. So what is the right way to do water treatment? I'm not just talking about not getting a panic plant here. What is the right way? To do water treatment, first you need time. You need time and you need the services of experienced water people. You cannot replace experience with literature. I've written dozens of papers and I can tell you that in a paper that's 10 pages long, I can only put a fraction of what I learned on that project. And so if somebody is reading that paper and trying to design a plant based on that, they're missing a lot of key information. The most important thing, I mean, quality and quantity, the correct design criteria for the plant. You cannot start building a plant without having a design criteria. And the design criteria, you have to define your raw water quality extremes. So your high concentrations and your low concentrations. Sometimes the low concentrations are the ones that are harder to treat. And you also have to define your maximum water quality that you have to deal with. In Canada, it's enforced that you have to design for a 1 in 100 year recurrence event. Different provinces have different limits, but in Quebec, it's very detailed. This occurs during the spring runoff. You have to establish your treated water objectives. Like I said, this may be imposed, but you may also have your own, and your treated water may also be for recycle. The hardest part of this is that you can't just do it based on the water that you've had for the past year, or the water that you have now, or the water that you had for the past 10 years. You have to figure out, estimate as best as you can what your conditions are going to be for the next 10 or 20 years. Nowadays, there are contingencies put into a treatment plant sizing because of global warming. We expect to have greater rain for high or low recurrence events. So what else? This is the second of 2 pages on the right way. So when you have the water, you do the stepwise testing. You analyze your water, you make sure you get some representative water. You do some laboratory testing with that water, and then you have an idea of what reagents you want to plan your pilot test. You do your pilot test, you know exactly what you need. If you do your pilot test, you know what reagents, you know how much solids you're going to create, you know what your effluent quality is going to be like, what pH you want to control to, what retention time you want. Once you do pilot testing, everything is good. You don't necessarily always have the water and the time for pilot testing, and I'll talk about that in how you can still prevent from having a panic plan. So when you do it right, your resulting treatment plant will have the right reagents, the most economical and efficient reagents with the right systems. You'll have the right retention times for your and designs of your reactors and your clarifier. Your agitation for different slurries have to be agitated differently, whether you have air or not. In a lime sludge mix tank in an HDS plant, you need to have a different agitator than what you have in other locations. Your aeration, if you're pumping sludge is very viscous. A standard slurry pump is not going to do it for you. You need positive displacement pumps. And also instrumentation, you cannot believe, if you put a pH probe on top of your reactor where you have your acid and your lime coming in and it's all being mixed, your pH is going to go up and down. Your pH probe has to be at the outlet of the reactor. And this is critical for a successful plant. Sludge density measurement, turbidity measurements. You can't put a turbidity just in a clarifier. If you have scaling issues, your turbidity meter is going to scale, and within 24 hours, it won't be reading right anymore. So there are surface scatter turbidity meters that you can use. So how do you avoid the pilot plant? Especially for a new mine, defining the water quality and quantity is not easily done. But you have to start in pre-feasibility, and it's not expensive. It's not a lot of time in pre-feasibility. Your water expert is just going to tell you some of the steps that you have to do. Some of these are just with the cores. I mean, you're already drilling to try and define your ore body, and then you're doing the mineralogy of these cores, but you also have to do acid-base accounting of the gangue minerals, what's up and below, and also what's going to be your tailings. You do humidity cells, you do leach tests, and if you do a lot of samples, if you're borderline, that's going to help you a lot. So when you do flotation, mineralogical studies, whatever it is that the ore body is, when you do flotation, you should also study the water. So you do your flotation cells in a pilot plant, and then what you do is you recycle that water and bring it back to the front of your pilot plant. This will tell you if you're going to make thiosalts. This will tell you where your sulfate is going to go up. This will tell you if you have salinity. And also for your flotation test, it'll be more representative. So it's a good thing. Excuse me. For the boreholes, after you've done your borehole, you use water for drilling. You purge the water out and you check the water concentration. And you see if you have any salinity in that water. And this would also be useful to have a baseline if ever there is some accusation of contamination in the future. So this is not a panic plan. It's just a pretty picture. But one of the things you got to do is in your mine project stage is do a detailed hydrology and hydrogeology. And you plan to keep clean water clean. This hydrology is going to tell you how much water you're going to have to deal with. When you can't have the water, you can still benchmark for quality. Benchmark means you look at other mines and you look for ore bodies that are similar to yours, and you see what they have to deal with, and you get ready for that. So nickel, lead, and zinc mines often have thiosalts. All of these mines that use flotation, they often have high sulfate in the process water. Gold mines have cyanide and ammonia. Iron mines have high suspended solids. Diamond mines as well. And I could go on. These are just some examples. So what else do you have to do? This is the last slide on actually avoiding the panic plan. Once you have your hydrology, hydrogeology, and you have an estimate of your chemistry, now you have to better define the quality and quantity through a mass balance. This is not always done. It's preferably done, and there are good tools for this now. And once you have the tool set up, it's also going to be useful during operation. And if you use this tool, then you have a very solid design basis to make a design criteria for your treatment plant. Now, I am going to talk in the next slide again about the combination of flows and ponds to deal with your high flow events, because it's not just the flow itself, because you can hold back some water. And one of the things you can do to avoid a panic plant, when you're building your mine, instead of raising your initial tailings dam for the first 2 or 5 years, you raise it for the first 10 years right away. And what this allows is a lot of water being held back, so you know exactly what the challenges are, and you can build the right plant right from the start. Now, I just want to mention the treatment sizing. When you build a treatment plant, the cost of the treatment plant is basically on the flow rate. And that's why it's important to optimize your treatment plant and your storage. This is the second and last technical slide. So on the y-axis, we have the costs. And here, there's no units, but we have the plant flow rate. So your treatment plant has to have a minimum size. So there's no zero, but the minimum size might be your average yearly flow. If that's the case, you need a very large pond. So your cost of your very large pond and your small treatment plant would be a total here. If you design your treatment plant to be able to take everything that happens, then your treatment plant's going to be very large, very expensive, but you have a very small pond. The pond never goes to zero either. But you do this analysis and you cost out different size of ponds and different plants. And what you find is that there is an optimum plant size that is best for your site. So this is the only example that I have here for new mines, because I want to focus on operating mines. So this is a new mine in the northern area that, as per local regulations, they used the cores, they did the acid base accounting, and they did the humidity cell tests. The engineering company that did the EPCM contract for the mine and the mill didn't have a specific water treatment expert. And the company stated that there's no problem with the contact water. After 2 years, the contact water was not acid, but the nickel concentration was about 10 milligrams per liter, when the discharge limit is 0.5 milligrams per liter. So this problem was noticed late, and the waste rock pile was basically almost surrounded by the pond. So there was no way to treat the water on the way into the pond. So the immediate cost of solution was that another dam had to be built, and lime had to be added. And lime, this is a remote location, so lime is very expensive, and the efficiency here is very low. So that was a very high cost for a few years, until the eventual permanent solution was put in place, which was also a high cost solution. At the same site, they never expected to have thiosalts. And the only reason they knew that they had thiosalts was when they failed the toxicity test at the effluent of the mill site. So that was a non-compliance event. So then they had to build new ponds for retention time and a new reagent systems that weren't planned from the beginning. And a non-compliance right away can affect your social license to operate. Now I'm going to have 3 operating mine examples. One operating mine with a treatment plant discovers some new ore nearby. This happens very often. And so the mine expands. The local government, well, they've always been in compliance, no problem. So the expansion is permitted. There's no environmental reason to prevent it. But with this expansion, you have a much larger footprint. And so with a larger footprint, you have more contact water. And then you have a high runoff event, not a very high runoff event, just a spring thaw. And you find that the pond system is too small, so that the solid liquid system, the solid liquid separation doesn't occur. Your reagent system is under capacity, so you need to add pumps. And your large water pumps can't keep up, so you need to get temporary pumps. So And this can be prevented. And I'm going to talk about some of the prevention you can do. Another example, an operating gold mine. This is actually common. I've seen it at more than one place. So in a gold mine, you use cyanide. The cyanide goes to the tailings pond, and so does the ammonia, which is a byproduct of the cyanide destruction. And these two are just degraded by being open to the atmosphere. So you need some retention time for this degradation. But then as the capacity in your tailings pond is taken up by tailings, so you have a tailings pond that's half full, you fill up your tailings pond, that leaves less space for the water. So you have a lot less retention time for the water. What happens? You have toxicity at the effluent. You have non-compliance for cyanide of ammonia.